Person ID aims at retrieving a person of interest across multiple different cameras, which may or may not have any field of view overlap. One of the most important applications we can find person tracking. Also, personal ID can be applied to video surveillance and forensics. Generally, if we want to deploy a ReID system, it will look like something like this. We have an original video frames captured by different cameras. Using a person detection model, we want to detect the people in the video frames. Then we annotate them, annotate the cross-camera labels to get a gallery of person images. Then we train a ReID model to learn discriminative features. This step is the core for developing a ReID system, and it is also the most widely studied paradigm in the literature. In the inference stage, given a person of interest or a query and the gallery set, we extract the feature representation using the ReID model learned in the previous stage. And at the end, we return the retrieved ranking list by sorting the calculated query to gallery similarity. It is likely that the top ranked persons are the target people or are the target person. Person identification is a very challenging problem because in the gallery, we have multiple images of each identity and each are captured by different cameras. So we would observe intra-class variance within the gallery. For instance, we observe pose change where the same ID can appear in the different cameras with different poses. Change in illumination, some images are captured under very bad illumination condition, which makes the extracting visual information very hard. Scale change, where the bounding box can be very large in some cases. And finally, the occlusion, where the same body, some body parts sometimes are not fully visible. For example, here, the pedestrian is covered by this whiteboard. To this end, most existing personal ID methods can be classified into three parts. Supervised learning, they mainly focus on metric learning and view invariant features. Here, label data is fed to the model and the classification loss like cross entropy is used for training. And each class here represents a single ID. However, the scalability of this method is very limited in the real world, where collecting a tremendous amount of labeled data is expensive. To alleviate this limitation, unsupervised learning adaptation were proposed. Here, the knowledge is transferred from a labeled source dataset to an e-labeled dataset. Similar to supervised learning, these methods suffer from the need for collecting annotation for the source datasets. The last approach is pure unsupervised learning, where no labeling is needed. Therefore, it is considered one of the most practical methods. And our work aligns with the pure unsupervised learning approach. We propose, in our work, we propose a novel method to encode both human body structural information and the temporal information to accomplish unsupervised ReID. To do that, we employ GCN to model the interframe and intraframe relations between pedestrian body joints. By combining these two relations, our framework is capable of alleviating the occlusion and visual ambiguity problem. Finally, using this new architecture, our model is capable of improving over the state-of-the-art method. Inspired by the recent success of path-based ReID methods in dealing with the occlusion problem, the goal of this module is to extract semantic features of key point regions. Specifically, given a tracklet of person sequence V, we randomly sample T-frames from the input video. We first utilize a pre-trained CNN model to extract a feature map for each of the frames, where Fi here is the feature map of the frame I. Then we fit the same tracklet to a pose estimator model to get a heat map of key points MKP. For the human key points model, we use HRNet pre-trained on the COCO dataset, a state-of-the-art pose estimator model. The model predicts 17 key points and we fuse all key points on the head region and get a final 14 key points, including head, shoulders, elbow, wrist, knees, hips, and ankles. Through an outer product and the global average pooling operations, we can get a group of appearance features, xk power s, for each of the key points in the frame, where k here is equal to 14. That's for video with t frames. The total number of local features we get is t multiplied by k. Inspired by the benefits of modeling the structural relationships among human body parts, we construct a spatial temporal graph on person sequence with K joints and T frames, featuring both intra-frame and inter-frame connection. We define X as the set of nodes where, in our graph, where each node Xi corresponds to a key point in the frame. And in order to model the relationship among different key points, we propose two types of edges, intra-frame and inter-frame edges. Particularly, the adjacent joints in the same frame are connected by the intra-frame edges. So there exists an edge between I and J if Xj is in AI, where AI is the collection of adjacent nodes in the same frame for node Xi. So this natural link captures the local dependencies, which may miss the temporal correlation of the joints. Therefore, we introduce the inter-frame edges to connect the nodes of the same body joint across adjacent frames. An edge exists between node I and K if xk is in the Ti, which is the set of nodes of same body parts in adjacent frames. So after obtaining the graph, we adopt GCN to leverage the contextual information from the neighborhood and then update the original feature iteratively. To implement a GCN on the human skeleton, we define the adjacency matrix A as the stack of different adjacency matrices AI of each frame. And for the GCN to work properly, we need to normalize nodes with large degree in the adjacency matrix using the following formula, where WL here is only the weight matrix of layer L. And after applying the spatial temporal GCN, each of the node features will get updated according to its adjacent nodes. And given the updated key point features, we use a spatial temporal attention to reflect the importance of each region in the final tracklet representation. And as a result, each spatial region Xi will be assigned with a different attention score. In order to train our model in a fully unsupervised manner, it is essential to design a supervision signal. To achieve this, we need to generate pseudo-labels using a clustering approach. In this work, we perform hierarchical clustering with randomly selecting PIDs and K-axes. And since we don't have down-to-earth labels, we assign each tracklet to a distinct cluster. Initially, the number of clusters C will be equal to the number of tracklets. Then, at each iteration, we merge a specific number of clusters using the distance between them. Each time, the clusters with the shortest distance are merged. Hence, we define the merging rate MP to measure the speed of clustering. Finally, after clustering, the new pseudo-labels, generated pseudo-labels, are used for retraining the model. To optimize the model, we use the half-batch triplet loss, and to meet its requirements, using clustering results, we generate a new dataset with PIDs and K images. This helps distinguish hard examples. The overall objective function of our framework is formulated as the sum of two hard-batch triplet loss and the softmax function of the clustering. To evaluate our model, we use two main video datasets, mass datasets, which is a very large-scale video dataset captured by 6 cameras on a university campus and contains around 20,000 video sequences, and do contain C datasets, which is also large-scale video reality dataset captured by 8 cameras, contains around 5,000 tracklets and 1,812 IDs, and containing around 702 IDs for training and the remaining for testing. For the implementation details, we use ResNet and we use HRNet as the post estimation model. We randomly select P equal to 4 IDs and K equal to 4 images. And then our optimizer is Adam, and the training epochs are 70. To validate the effectiveness of our method, we compare our proposed method with several state-of-the-art methods. On Mars dataset, we get the best rank of 58.5% and the best map of 34.1%. And on DocumentTFC, we get the best rank 1 equal to 76.5 and the second best map of 65.3. We show the impacts of 3 learning components in figure 3. So with the cluster loss, our model achieves a marginal performance of 27.1% in map. The addition of the global hard triplet loss and the key point triplets loss significantly improves the performance to 34.1% in map and 58.5% in rank 1 score. This is an illustration of our model retrieval result on DocumentTMC video ID dataset. The leftmost image is in each panel is the query image. For the 5 columns, they show the top 5 retrieval results. The true match is annotated by the gray bounding boxes, and false match is annotated by the red bounding boxes. We can see that our model successfully returns the correct matches, but sometimes gets confused when people are wearing similar clothes. To summarize our contribution, we propose a fully unsupervised ID framework to learn interframe and intra-frame relation information for discriminative feature learning. By jointly optimizing the GCN, our framework is capable of well capturing the semantic relations between key point regions across frames and alleviating the occlusion problem. We improved considerably over previous ID methods. Thank you so much for your attention.
Thank you, Khadija. She can answer to your question. Somebody from the audience has some question. Okay, Khadija, you're still there?
Yes.
So no question. Maybe I have one curiosity. How critical is the resolution for the performance of the key point estimation that you are using? Because I imagine for identification, the resolution of the people is quite small, right?
Yes, that's correct. The resolution of the images is a bit small. So in the case of the data sets I'm using, it wasn't a big problem because I was using the state-of-the-art post-estimation model, HRNet. So it gives me like kind of a good poses key points. So use like a different data sets, for example, data sets captured by drones or like something similar. I guess the resolution would be like very small, and the key points won't be like the performance of the post estimator models won't be as good as as it should.
For answering to the question, I think we can welcome the next speaker that is here. Is Davide Alessandro Coccomini, combining efficient net and vision transformer for video deepfake detection. So let's welcome the speaker. Perfect, please.
And I am Davide Coccomini, and I am a PhD student at University of Pisa and a research associate at the Italian National Research Council in Pisa. And this is the presentation of our research work called Combining Efficient Net and Vision Transformers for Video Deepfake Detection. This is a brief outline of what I will talk about today. In particular, I will start with explaining what is a deepfake. Then I will show you our deepfake detector that we call the cross-efficient vision transformer. Then I will show you some scale and security issues in deepfake detection field and how we proposed to solve them. And in the end, I will present several results and conclusions from our paper. So let's start with what is a deepfake. A deepfake is the result of several deep learning techniques that allow us to manipulate an image or a video, and in a situation like that, you can see that we are able to manipulate a target actor, exploiting a source actor in the way that the target one move and speak in the same way of the source actor. And this may seem to be something interesting and maybe funny, but we should care about deepfakes because they may be used to destroy the people's reputation. They may be used to undermine the justice system, for example, creating fake evidences during a judicial process, and even cause tensions between countries. And just a few weeks ago, we have seen this video that is the first time in which a deep fake is used during a war. This is a video of Zelensky, the president of Ukraine, that say to his troops to give up during the current war. So this is really an important problem to face. And in general, when we try to identify if a video is a deep fake or not, we try to detect, to notice this strange situation like the glasses, the strange mouth of this guy. But the problem is that in these years, we are seeing more and more approaches that allow us to obtain credible results like that one, in which probably the majority of us will never notice something strange. So, the previous works in which about we inspired for our research are mainly based on a convolutional neural network that is called EfficientNet B7, and the popular deepfake detector is based on these four the EfficientNet B7 networks that took as input the faces extracted from the video, and each face is classified as fake or not. And if the majority of these networks say that the face is fake, then it is considered fake. And the same is done for all the faces inside the video, and if the majority of the faces are fake, then the whole video is fake. So, but we want to exploit different architecture, that is the transformer, that is an architecture introduced in natural language processing in 2017, but in 2020 came into the vision field with the vision transformer and with other variants for video understanding, and is obtaining a lot of impressive results on several computer vision tasks. So we asked, can we design a novel deepfake detector that exploit together EfficientNet that obtain very good results in deepfake detection and the vision transformers that seems to be so powerful on several vision tasks? To do that, we decided to combine them using EfficientNet as a patch extractor. What does it mean? This idea starts from the functioning, the internal mechanisms of vision transformers, and in particular, the first step when you want to use a vision transformer for classification is to split the image in several patches. Then these patches are projected in tokens, and these tokens go inside a transformer encoder, multi-layer perceptron, and we get the classification. But the process of starting from a large image and go into several smaller images is something that can be similar to what happens inside a convolutional neural networks. So we start with an image of large dimension on free channels, and you obtain at the end of the convolutional layers a lot of images, just splitting the resulting image on the channels. So what we proposed with the first version of our deepfake detector is the efficient vision transformer that consists again in the extraction of faces from the video. Then the face, instead of being splitted in patches, is passed into an EfficientNet B0. that return us the patches that we need. So this is important because this is the smallest one of the efficient networks in order to obtain a light network, light model. And also this is a learnable process. So we do not just split the image in patches, but we transform the image into patches. And then you have the transformer mechanism in order to obtain the classification. But here we have a problem. These are small patches, so we are limited to one side of these patches. So we created a cross-efficient vision transformer that consists in two branches, one with a deeper efficient at B0 and one with a smaller efficient at B0. The first one returns us a lot of smaller patches more transformed, and the second one returns us the larger patches but with a lower level of transformation. Then we have two different transformer encoders that communicate through a cross-attention mechanism, and in the end, with a multi-layer perceptron, we obtain the classification that we need. But having a good model in this deepfake detection field is not enough, because we have to manage also particular situation, edge cases. For example, in this case, we have two people inside the video. And traditionally, what happens is that we extract all the faces from the video, we classificate each one of them with a value that starts from 0, which means that the image is not a fake, and 1, that it is manipulated. And we perform the mean, and if this mean is higher than a threshold, for example 0.5, then the video is fake, otherwise it isn't. But as you can see in this case, the girl obtained high values, but because of the low values given to the guy, such as this one and this one, we obtain a low mean value. So our proposal is to improve the classification and evaluation strategy, classifying the faces based on the person and obtaining two, in this case, different classification. And if even one of these obtain a value that is over the threshold, then the whole video is fake. And another problem is the scale one. So when you want to classify a video, you have inside the video a lot of different faces extracted from different frames. But we asked, which is a good number that allow us to obtain a good level of accuracy, and which is the matrix, and do not use too much computational resources. So we conducted this study in order to understand the variation of the F1 score using a different number of phases inside the video. And as you can see, in general, for a video of 10 seconds, you have that using 30 images, 30 faces, is the same of using 80. And so you do not have to use all the faces that you detect inside the video. And also using a small, very small number of faces, as you can see, the F1 score is not too different. So when we put these systems inside the real world, we have to manage also this situation. This is some results obtained by our model on face forensics official test dataset. This is a video level accuracy. And this is the same the evaluation conducted on the FDC official test dataset. And as you can see, we obtain similar results to other model, to other important model, but with a really small number of parameters. And this is important because we want that these systems go into the real world. So just to give you some conclusions, what did we discover? We discovered that vision transformers are very good in deepfake detection, that combining efficient and vision transformer is a winning approach, and that a good model is not enough, but we have to manage also security and scale issues in order to obtain a model that may be used also in the real world. So thank you for your attention, and if you have any question, I'm available, or you can find the code of our research on GitHub and reach me out on LinkedIn, Medium, or write me an email. Thank you very much.
Thank you for the presentation. Any question from the audience? I may have a curiosity on your relevant question. Sorry.
Okay.
The question that you said, how many phases I need, how this evaluation was conducted, because can imagine that different type of videos have a different answer to this question. So I would like to hear a bit more details about it.
Okay, thank you for the question. We conducted our experiments just selecting, we primarily detected all the faces inside the video. Then we selected faces inside the video with similar distance in time. And then we started testing the model using only 5 faces distributed inside the video and see the F1 score. Then we have done the same with the 10, 20, 30, and so on. And we have seen that there is this curve that at the end, after 25, 30 number of faces for this type of videos, start to remain the same, up to 80, that is our last experiment. And so this is the range that we detected during our experiments.
Do you expect a difference when you change data set or something like that?
This may change based on the FPS and on the length of video. And also another thing that may change our results may be in the movement that the people do inside the video and the detection. So this may be quite can depend also by the dataset, but we used the FDC that is quite has a good variety of situations and videos. So this may be similar also on other dataset.
Thank you very much.
Thank you.
Let's thank the speaker again. So we will have also another presentation here from Alex Falcon. He's here. Alex? Yes. The title of the next talk is Learning Video Retrieval Models with Relevance-Aware Online Mining. So let's welcome Alex Falcon.
So, hi everyone. I'm Alex Falcon and I'm a PhD student at the University of Udine and Fondazione Bruno Kessler. Today, I'm presenting our paper called Learning Video Retrieval Models with Relevance-Aware Online Mining. So, every minute, several hundreds of hours of video content are uploaded to the internet, which means that we need intelligent methods to look into this huge amount of data and retrieve the videos which the user is looking for. This can be framed as a text video retrieval problem, which means that given a textual query, we want to rank all the videos based on how close they are to the user query. As can be seen in this example, we have that the contents of a video can be captured by multiple captions. And similarly, we have that multiple videos can be captured by a single query. This means that in order to understand whether a video retrieval system is working well or not, we have to look at the quality of the full ranking list, which puts us closer to the semantic text video retrieval task. This task is supported by the usage of rank-aware metrics, such as MAP and NDCG, which is different from the typical retrieval setting, where only record rates or mean, median rank are used as evaluation metric. In the current and typically used methodology to learn video retrieval models, 3 ingredients are typically needed. First of all, we have deep neural networks to compute independent representations for both the video and the captions. We have large annotated data sets. And finally, an optimization framework, which is typically implemented with a contrastive loss function, such as the triplet loss, which is shown on the right. This loss aims at learning a joint embedding space by increasing the similarity, measured with a function S, of a video V star with all of its captions Q star, while at the same time decreasing the similarity with a negative caption, Q minus, that is a caption which is not associated to V star in the dataset. Visually, We have V-star, we have Q-star, we have several other captions in our embedding space. And the main question is, how do we select Q-? A typical approach is called R-negative mining, which means that we want to look at the negative captions and pick the one that in the current network state has the highest similarity to the video. In this case, pick a bottle of wine is selected, which means that after learning, we may reach a situation such as the one shown on the right, which intuitively can be interpreted as V-star being more similar to close the fridge than it is to pick a bottle of wine, which is clearly not an ideal situation since pick a bottle of wine should be treated as a valid caption for the video. So first of all, what we observe here is that the typical methodology used for text-video retrieval does not transfer well to semantic text-video retrieval. To understand this, we want to look at two additional notions, which are a relevance function, which is, let's say, a function that gives us a percentage, which tells us how much close two captions or videos are from a semantical point of view. And this is typically implemented with verbs by looking at the verbs and nouns found within the caption. And then we also introduce a threshold tau, which we use to separate in our definition the relevant from the irrelevant content. So if now we look back at the previous equation, we can observe that we were picking Q inside a set which may actually contain relevant captions for V-star. And in fact, we saw that pick a bottle of wine was also one of the valid negative captions. Now, what we propose in this paper is a relevance-aware negative mining technique, which is an improvement of the previous, the typically used mining technique, which uses the relevance definition to actually filter, as can be seen here, to actually filter out all those captions which do share a high relevance, higher than tau, with V-star from the negatives pool. In this case, it means that pick a bottle of wine is now excluded since it has a high relevance to V-star, whereas at the same time, close the fridge has a low relevance, so it is still a valid negative caption. Now, with this one, we, let's say, deal with the negatives. At the same time, we have all those relevant captions which are not associated to the video in the dataset, and these are completely not used during the training process. This means that we want to actually introduce them within the learning process, and to do so, we propose this additional technique. First of all, we identify the hardest positive at each iteration, which means that, again, we use the relevance and tau to identify and to create actually a pool of relevant items which can be used for the learning process. So in this case, we pick the caption which has the lowest similarity to the video, since we want to pull it closer to the video, which means that we also need an additional loss term, which actually increases the similarity of Q+, so the identified positive, with the video V-star. In the previous example, this means that, for example, pick a bottle of wine is selected, which means that after learning, we may reach a situation in which both Q* and Q+ are closer, so have a higher similarity with the video in the embedding space. By putting together this technique with REN, the previous one, we introduce what we call the relevance-aware negatives and positives mining technique, which we call REMP. So in this case, to validate our methodology, we use two public data sets. First of all, we use Epic Kitchens 100, which is a large-scale data set of egocentric video clips, which capture activities inside a kitchen. In this case, each clip is captioned with one description, which contains one verb and at least one noun. And in this case, for Epic, we use the caption classes as the video classes, which means that, for example, in the example on the left, it means that, for example, the class take is used both for the for the video and the caption, and this class contains take as well as all its synonyms, such as pick up, grab, and so on. Then we also use MSR VTT, which is a popular benchmark dataset, And in this case, we have that the videos come from multiple domains and multiple sources. Moreover, in this case, we have 20 captions for each clip, which, differently from Epic, have no guarantees on how many nouns and verbs can be found inside each caption. And in particular, since we have multiple captions per video, we define the video classes as the classes which are popular among the captions. So, for example, woman may be a valid noun class, whereas, for example, actresses may not, since it only appears once. So a first experiment that we perform in order to support the utility and the usefulness of our approach consists in analyzing how many relevant captions are actually treated as negatives during the learning process. On Epic, we observe 4 modes. First of all, we can see that 45% of the captions are actually completely irrelevant, so they do not share any noun or verb class to the video. On the other hand, this also means that more than 50% do actually share at least some of the captions, so they are at least partially relevant to the video. And in particular, around 13% of them do actually share the same classes as the video. On MSR, this is clearly different due to how we decided to identify the video classes, which makes it hard for any caption to reach a high relevance to the video itself. Nonetheless, we can see that around 15% of the captions should be treated as valid, relevant captions to the video. So those modes that we identified in the previous slide can also be used, and we actually do use them, as the possible values for the threshold tau. So on Epic, what we observe is that by using, for example, a high threshold of 0.75, which means that we are only excluding the really highly relevant captions from the pool of the negatives, we actually observe already an improvement in both the considered metrics. Furthermore, if we decrease tau and increase, therefore filtering more and more captions from the pool of the negatives, we actually observe improvements of up to 13% in NDCG and around 7% in MAP. Moreover, if we also introduce the positives in the learning process, we observe improvements of up to 23% in NDCG and almost 8% in MAP. On Epic, clearly, if we use, as mentioned before, a high relevance, so a high value for the threshold, we won't find any caption that has relevance that high. Nonetheless, if we use a low value for the threshold, and so we identify at least a few captions which can be removed from the pool of the negatives, we observe improvements of up to 3% with RAN, with the first technique, and almost 6% improvement with the second technique. Now, here we perform a comparison to other methods on both the data sets. On Epic, we compare to 4 methods, which include the 3 methods that currently form the public leaderboard of the challenge on this data set, and also HGR, which we use as the baseline in our experiments. So if we compare with the 2 best performing methods, we observe consistent improvements of around 5% in NDCG and around 3% in MAP over the previous current state-of-the-art methods. On MSRVTT, we compared mostly to 2 methods and our baseline, which include collaborative experts and mixture of embedding experts, which are 2 methods that are often used as a baseline methods on MSRVTT. In this case, in particular, we observe improvements of around 2% when compared to collaborative experts in this case. So in conclusion, what we observe is that the current methodology, which is typically used to learn video retrieval models, does not transfer well to semantic text video retrieval. And we show that this is mostly due to the fact that the non-irrelevant captions, so captions which at least are partially relevant to the video, are wrongfully treated as negatives. To address this, we propose RAN, the first technique, which uses the relevance to avoid these false negatives, let's say, during the learning process. And then we also introduced RAMP in order to also use the relevant captions, which are not associated to the video in the dataset, during the learning process. And then we compared with state-of-the-art methods on both datasets and achieved considerable improvements. And finally, we uploaded all the code and pre-trained models at this GitHub link. And thank you for the attention.
Thank you, Alex, for the presentation. Some questions from the audience? Yes, please.
Thank you for the talk, Alex.
Thank you.
Is this task aligned with the evaluation of the Epic Kitchens 100 we have a Has Challenge online? Okay. And if so, are you using the leaderboard? Are those results there? Thank you.
Thank you for the question. So yeah, they are aligned with the challenge. I mean, I'm using their the evaluation protocol used by the dataset collectors, the challenge organizers. At this time, I haven't uploaded yet this the prediction, let's say, for this model, but we are currently working on, let's say, an ensemble technique with both this method and another one, which I think we currently uploaded it to the challenge since we plan to participate. But I think right now it's still set on private. So maybe that's why you don't see it yet. Thank you for the question.
At this point, I would thank the speaker since we are a bit tight of schedule.
Thank you.
Thank you. So I think the last speaker will be remote, right? But maybe available for question. Is it correct? Fuma, you are here?
Hello.
Hello. Okay, I think we can play the video as you requested, and then please stay there. Okay.
Hello everyone, I'm Fuma Kinshima from Host University. I'd like to present our work on frame adaptive rate control scheme for video compressive sensing. I'll talk as follows. To transfer all obtained signal information, enormous electric power is required, so it is significant to compress the data before transmission. Compressive sensing is one of the attractive data sampling methods. The image is multiplied by the sampling matrix, then obtain the image in low dimension. It is often called measurement. This method can sample and compress at the same time. After transmission, image can be recovered by applying reconstruction algorithm. But CS still has a problem. That is to sample only once from the entire frame, and the measurement has a lot of redundancy. So such a method is mainstream. At first, divide the frame into several smaller square blocks and sample from each block. Because the sampling area is smaller, sampling is easier and allows data to be read faster. Then employ prediction-based coding algorithm, and the difference between the current measurement and predicted measurement are quantized to reduce the data size. But if the compression is not sufficient, data can't be sent because the internet limits bandwidth. So compressed data must be smaller than it, and under this condition, we want to maximize the data quality. Hence, we back to the encoder side and apply control system. In quantization, we use quantization parameter QP that decide how much compressed data. QP directly affects compressed data size. For example, if QP is higher, image can be reconstructed phase-free, but file size will be larger and less likely to be able to transferred. Therefore, it is necessary to use an appropriate QP. The task deciding QP to be under available bandwidth is rate control. This is a related work of rate control. It has two-step rate control algorithm At first, roughly decide a QP candidate, and then optimal QP is searched by iteration. But this method has a lot of calculation, take long processing time, and only hand images, so we propose a way that solves this problem. This is our overall system figure. We use block-based compressive sensing, prediction, and quantized residue data YR. After rate control, data is transmitted, decoded, and reconstructed. I talk rate control part in detail. First, I talk about quantization. This is quantization expressed by mathematical formula. Round function rounds the float value to the nearest integer. Residue measurement YR is divided by delta. Delta is defined using QP like this. N is the number of bits. The numerator of delta means the capacity that can store the residue measurement. If the residue measurement is larger than this value, it is cut to this value. After transfer, dequantization is required to recover the original signal. The calculation is like this. The quantized value is calculated so that it is close to the residue value. This 0.5 means bias. Triangle threshold method is often used for making a white and black image. At first, connect highest value and lowest value, not 0. Then draw a vertical line to this line and find the longest vertical line, D, and decide this is a threshold value. We use this method to find controllable QP. To do it, we set as number of pixels equal number of delta candidate and brightness equal size of delta candidate. We find delta candidates like this. We calculate delta changing QP equals 0, 1, 2 until delta equals 0. After that, adapt triangle threshold method to this array and get optimal QP. We can get it with less iteration. Using triangle threshold method for all video frames increases the amount of calculation, but because adjacent frames are similar in video, we can find the optimal QPC, which is for the current frame QP, from close to the QPP, which is for the previous frame QP. Calculation is like this. Where I is initialized with 0, we add 1 to QPP and reduce it by 0.5 until total bit consumption is less than bit limitation. Even with the best QPC, there is a difference between the finally obtained bit consumption and bit limitation. If that difference is small, we can transfer efficiently. We propose that the sum of this difference and bit limitation is the bit limitation of the next frame. It can be expressed like this, where k is the number of frames and wk is the difference. By changing bit limitation for each frame, we can efficiently transfer with a small amount of calculation. After QP is decided for the current frame, block-based QP refinement is further processed. At the time of compression, quantization is performed block by block. The range of this calculation, which means the difference between the dequantized value and residue, is from minus QP divided by 2 to QP divided by 2. If this difference is large, a lot of information will be lost when data is transferred, so we'll give this block a little bigger QP like this, where I is initialized with 0. If QP is changed too much, the quality of reconstructed image is deteriorated, so we change it a little like this. If rate control isn't realized when decreasing by 0.01, QPC is applied to all blocks. Before showing results, I explained the experimental setting. All the experiments are implemented using MATLAB 2021A. The proposed coding framework is based on block-based compressive sensing and intra-prediction. We use the inverse discrete fast Walsh-Hadamard transform and L1 minimization to recover the sparse measurement. Datasets are WildTrack and MCLJCB, which includes some video dataset. At first, I show the quantization performance comparison with QP equals 15, sampling rate equals 0.5, and the number of bits equals 16. On average, our algorithm achieves an average PSNR of 29.80 decibel and an average BBP of 1.93 BPP. We report the improvement of up to 7.66% BPP reduction in image Barbara and an improvement of 12.87 decibel PSNR in image women. Compared to the previous works, this work obtained the highest PSNR for keeping a similar compression ability. This figure illustrates the average PPP up to each frame with sampling rate equals 0.5, block size B equals 16, and bit limitation equals 0.5. We use the same measurement matrix and intra-prediction. Therefore, only the rate control algorithm is compared. For video rate control, it doesn't matter if a frame BPP is larger than bit limitation, and the average from the beginning to that frame should be less than bit limitation. We can find rate control can't work if QP is fixed all frames. Compared to the state of the art, it turns out that our result is closest to bit limitation and never exceeded that value. This table shows the comparison result of average PSNR for the entire frame and the processing time for all test videos with block size equals 16. We report up to 53% minute reduction and an improvement of 1.41 decibel PSNR when bit limitation equals 1 and sampling rate equals 0.5. When sampling rate equals 0.75, our algorithm achieves a minute reduction of 40% processing time and an improvement of 1.56 decibel for this video set when bit limitation equals 1. This figure shows the visual quality comparison for the first frame to fourth frame compared with only the rate control part. This work has better visual quality than state-of-the-art under the same bit limitation constraint. Conclusion: this work proposed the frame adaptive rate control scheme for compressively sensed videos. As a result, the reduction of the processing time up to 53% and 1.56 decibel increase in PSNR compared to the state of the art. If you have some question, please feel free to contact me at this email address. That's all. Thank you for listening.
Thank you, Fuma, for your video. Are there any questions from the audience? I think it's already 6 p.m., so let's thank Fuma. Maybe you gave your email, so if people are interested, they can write to you. We have a very last session for today, so thank you.
Thank you.
So the last session for today is Deep Fake Images Detection and Reconstruction Challenge, and the chair of this session is Luca Guarnera from University of Catania.
Non c'è l'altro schermo.
Ah, ok. No, va bene. Okay. Good afternoon and welcome at the Deepfake Image Detection and Reconstruction Challenge. I'm Luca Guarnera, research fellow at the University of Catania.
and my research topic is multimedia forensics with a particular focus on the creation of a new deepfake detection method. Okay, the team organizer of this challenge is the Professor Sebastiano Battiato, full professor at the University of Catania, Oliver Giudice, research fellow at Banca d'Italia, Francesco Guarnera, postdoc at the University of Catania, Alessandro Ortis, research fellow at the University of Catania, Antonino Paratore, digital forensic expert at ICT Lab, spin-off of the University of Catania, and finally, the Professor Giovanni Puglisi, Associate Professor at the University of Cagliari. Okay, we start with deepfake. Deepfake refers all multimedia contents synthetically altered or created by deep learning models, generative models. And since their first creation, deepfake have been used for malicious purposes, such as in the pornography industry, or to spread misinformation. You can understand that it is necessary to contrast the illicit use of this powerful technology. But much work has been proposed in the literature, but unfortunately most of it lack generalizability. Okay, for this reason, based on this principle, the purpose of this challenge is to create the first one, an in-the-wild deepfake detection algorithm, and the second one is to try to reconstruct the source images from those deepfake. For this challenge, for the two tasks, we used deepfake images of people faces. Okay, we start with the first task. The objective is to create in the wild deepfake detection algorithm, and this task is a classical classification task with the objective to distinguish real versus synthetic data. The participant solution will be evaluated with a particular emphasis in terms of robustness to common alteration on images such as rotation, mirroring, Gaussian filter, scaling, cropping, recompression, and a combination between them. Okay, for the task one, we take into account as a real dataset, we collected images given from Celebay and FFHQ. As a deepfake dataset, we collected the images from these 5 GAN engine: StarGAN, AtGAN, GDVCT, StyleGAN, and StyleGAN2. The task, the rules related to the task one is reported in the slide. Participants will organize this dataset as they see fit. The participants print the dataset in the training and validation, define the split percentage and other parameters, and can perform an augmentation operation as long as they use only the dataset provided for the competition. The second rule, the test set released at the end of the competition will be a zip file composed by several real and deepfake images, similar to those of the training data, and in addition, images obtained by applying some processing operation like rotation, Gaussian filter, JPEG compression, and others. For this task, the winning team will be selected with respect to the highest classification accuracy value obtained on the real versus deepfake classification task, computed with the participant solution on a further set of data not available until the end of the challenge submission period. These are an example of the tested images related to the task one. You can see images with several tags like rotation, blur, and others. As regards the task 2, this task called source image reconstruction is never addressed in literature, and the goal is to reconstruct in the best way the original images starting from the deepfake ones. For this, in this case, we take into account the StyleGAN2 architecture, in which we create deepfake images. In detail, StyleGAN2 take two inputs, their source and a reference. The source is manipulated with the characteristics of the reference images. The objective is to take in input the deepfake images. The objective is to reconstruct the source images. But there is a complicated task, and we have a problem for the time, and for this reason, no team participate at this last challenge. Okay, we start with the participants. In this slide, so you can see the teams that participate at this challenge, and the first three teams are Vision Labs, DC Gun, and Team Nirma. Okay, in this slide you can see the classification accuracy value that each team achieved in this challenge. The last four teams are as reported in the slide. The third teams are the Team Nirma, and the winning team is Vision Labs. Okay, and here I think that there is connected Patel. No? I think. Sorry. Patel will describe the solution of the proposed approach. Or we can start with the Professor Marchalis.
He's here. We are connecting, promoting a member of the Zoom.
Okay. Okay, we start with the Professor Marchalis. Okay. The Professor Marchalis described the solution of your team. Con la porta USB. Bisogna togliere questa.
Well, thank you, Luca. Nice to meet you once again. My name is Gianluca Marchalis from University of Cagliari. In this case, I simply present the solution of my team, which was led in this case by Giulia Urru and other researchers of the Cagliari team. As you probably know, we are specialized on biometric recognition, so this was the first time we dealt with the challenging application of deepfake detection. Here I will give you only some details about our method for the simple reason that the whole method has been submitted for publication to the ICIP conference. So I can give you only some small details about. The claim is this one. Behind our approach, distinguish the artifacts present in the video image due to malicious manipulation from those of normal compression resizing. So the goal of our method is has not been born to recognize people in the wild, but in particular for detecting artifacts when videos or images are exchanged, are sent by social media. So, for example, using WhatsApp and other approaches like of the kind. Okay, The core of the method is a well-known transformation which is called discrete cosine transform. But we did not rely only on this well-known transformation. We follow two techniques. The one is to empower the feature vector by using by extraction from the image, additional information related to possible compression and resizing in terms of scale. And the second step of our approach is also to design an appropriate network augmented with the information coming from other images manipulated in terms of rescaling and resizing factors. So in this case, we have the main idea that I can summarize about our method. As you can see, there is an article, a conference paper, so we are currently keeping our fingers crossed because we did not yet receive any news about the acceptance of this paper. Just 2 bits about our network. Is an exception network basically customized for the task, because we have to embed in this network more information related to scale, to rescale and compression, JPEG compression information in particular. What I will show you in the next slides are related basically on the training set that the organizer of the competition released to us. So what you will see is a subdivision, classical subdivision of the training set released by the organizer in 3 data sets. The first for training the network, the second part for validating and activating an early stopping condition for the network, and finally, what the numbers I will present to you are related to the test set, the last part of the data set itself. In order to augment data, besides the approach to generate a novel feature vector, which we call tensor, a tensor-based approach to deepfake detection, we augmented data by using these tricks. So Gaussian filters, rotation flips, resize and JPEG compression, and in order to augment, to give to the network some more data, the usual approach which is largely followed by the most of researchers. In this case, we have the robustness to transformation. The test set, what remains of the training set released by the organizer, have been used as a test set, as a sort of test set. And the numbers I can show to you were very promising before knowing the actual position, which is not so much satisfactory, but this means that we have a lot of work to do in order to reach the top level in this application. So this kind of approach show what show that if we change the network, basically, we have a different accuracy, this is true, but more or less we have a sort of a convergence of this accuracy beside Gaussian filters, JPEG compression, flip, rotation, and so on. In this slide, we compared the result with the state of the art. In this case, we used the same training set adopted for training the network in the table, and we, by following the same experimental protocol, improved definitely the performance. As I said before, there is a lot of work to do. These are the basic precision recall curves, which are encouraging anyway, but what we want to show to you is some examples of, in the challenge data set, where our network failed. These images are all images are live image. The ground truth said us that they must be classified as live. But our network classified them as fake, okay? This is, of course, an error, a classification error. And these are just some examples, but we notice the same behavior in other cases, similar cases. And this suggests us that our network worked just as a general artifact detector. In the sense, there is not deep fake in this case, okay? But there are corruption artifacts. So the network, the point of view of the network was simply to say us, be careful, in this image is not perfect. There is something wrong in the image. Of course, this cannot be relevant from the point of view of the deepfake detection itself, but said us that anyway, a sort of artifact detector in other fields, in other applications, can be used. So this is the first conclusion we had just by seeing the results, the current results. A lot of work is necessary for improving the performance, even in the deepfake detection field in particular. So I'm very thankful to the organizer of this competition, who allows us to prove ourselves in this novel application. So thank you, and hope you will organize a novel challenge on the matter. Thank you.
Okay, other question?
Hi, good evening. The only question I have, and this is based, this could be from the organizers or from Professor himself. I saw 85-15 split on testing versus validation versus testing. Was that the organizers split, or did you choose that 85-15 split?
Hi. No, we provided a splitting of the data. Yes.
Hi. For the method presented, I have a question, Gianluca.
Okay.
Ciao. Hello. Okay. A couple of questions. First, you're using as a factor, if I got correctly, the DCT, right? Is there any, which basically you have a base decomposition, right, of information. Did you think that sparse coding, which is very popular, can learn better representation to solve this problem? This is at first. Or if there are methods based on such kind of things. And the second is about the data sets. At the end, I was asking myself, is this problem, well, is solved because intelligence, or because, as you said, probably is just a detector of artifacts? Are there possibility to test those methods not only on faces, because these deep fakes could be any image labeled or corrupted in a way that is perceived to be real, right? did you test, is there a possibility to test generalization of those methods? Even, well, if it's a fake, the same method should work for faces like this, but should work also for, I don't know, real versus generated images from synthetic domain, right? Is there any research that try to prove that those methods are really intelligent, because understand not only in the face space, but also in another space which an image is fake? Thank you.
Okay, Giovanni, thank you for the questions. They are very challenging questions itself, because they bring us in the old problem of all, for all specialized people in training neural networks. The problem core where training such kind of approaches is we are creating a good correlation between input and the target, or we are forcing some of correlation. So, for example, I said in our case that our proposal was a good artifact detector because many images in the test set were univocally corrupted in some way. So the system detected some sort of modification in images as well. In this case, I can say, for example, that we must be very careful and have a lesson to learn. We must focus very clearly on the model. We must improve the model and the hypothesis behind the model, because otherwise we can have results like these ones. That it's good that in some cases 60%, 60, 70% more or less of accuracy is not bad, because the data set, the test set released by the organizers was very, very challenging, was very difficult. Okay, so 70% may appear as a wrong number, but it is good because the test set is very difficult. We can see in other cases that this approach performs 90%. In this case, we have a strong correlation between input and output, between input and target. So in this case, the model was correctly prepared. But for the general problem of the fake, exemplified in this very challenging test set, this model is not yet ready. Okay? This is the point. This is the point. Of course, I don't know what the other participants did, especially the first three, the top three participants. I don't know what they did. So I don't know, for example, if they used a sparse representation, as you suggested in your first question. I think that in deepfake detection, we need models. We need hypotheses behind the model. In the wild is too difficult. It's still, because deepfake detection, deepfake is a problem born in 2018. In 2018, the first advices about the menace, the threat that deepfake can be, okay? So, we are in 2022. We cannot expect to solve such a difficult problem. Second, deepfake, when performed in this very challenging way, show to us that the attackers have a lot of possibilities. And it is very difficult to predict all the kind of artifacts that may add. In some cases, for example, artifacts can be added as well, simply after providing the deepfake in high resolution, we simply reduce the size or introduce some JPEG compression. And in this case, the system, which works perfectly on high resolution deepfakes, simply fail when you have to classify the same video, but resized or compressed. This is very important to understand, to be aware about this problem, which appears as a small problem. But when we have, let's think to worldwide communication among users. I want to attack a certain victim with a deepfake of him, and I send by social networks or by WhatsApp, for example, a deepfake. WhatsApp automatically reduces the size and compress the media. So if I equip my smartphone with a deepfake detector trained with high-resolution images, my deepfake detector could be in danger because it could fail its classification. The questions in the middle, sorry, Giovanni, I forget the question in the middle.
Deepfake because we are generating automatically images today, but this is an old problem, right? Mm-hmm. Because if you generate synthetic images with rendering tools, that could be a fake, right?
Mm-hmm. Of course,
okay.
artifacts.
So,
well.
What's the difference today and before? And if there is difference, methods that are working today because generating images with a neural network should work also with other kind of fake. So if a method is intelligent, should work for both. I don't know, that's probably I'm wrong, but if you are able to recognize fake, a method should generalize if an image is rendered and is not real, or if it's generated by a deep network. Because as you said, in this moment, you are just looking for artifacts, which of course, in this moment, any generation methods put artifacts in videos and so on and so forth. So probably, if you have methods that are able to distinguish real from fake on generated images from deep learning and on simulated images, could be more interesting to see why and search for the key insight that gives you a possibility to understand what is a fake.
I may agree with you in the sense that I'm a strong, in my opinion, we should start from the models. We know that deepfake are generated using, for example, generative adversarial networks and other methods of the kind. So we should better think to the specific artifact that such kind of methods can add to the images. And maybe, I don't know, I'm not sure, this kind of artifacts can be different from that we can add using other approaches. But I, frankly speaking, Giovanni, so far I do not have an answer to this. I think there is a lot of work to do. These kind of challenges help a lot in improving even more or less our knowledge about the problem, especially when we see the slide with that I showed you previously, for example. And so this kind of events are welcome because we got some more data, and we can use them to study separately the problem without immediately say, okay, let's train a network and let's see. Okay? Sebastiano. Thank you.
Yes, I have a comment also to answer to Giovanni, in the sense that now the problem of deepfake detection is very complicated because, as mentioned by Gianluca, okay, as mentioned by Gianluca, the research starts to work detecting artifacts generated by specific engine. But in this case, we tried to put together images generated by different GANs with the specific goal to put in the direction that you mentioned, generalization, because of course we need generalization in order to have strong and robust methods. And the research at the moment, of course, the goal is to separate synthetic images from real images in general context, but is a goal that is too far away from the current technologies. No? At the moment, the research group in the world are working on phase, because deep fake seems to be the most dangerous application of this technology when you generate forgery images. Okay? In general, of course, there are the possibility to study in advance, the engine that generated some signal to find artifacts, and the majority of the works in the field tends to specify what kind of artifacts each specific engine are introducing in the signal. When you put together signal computed from an engine that you don't know in advance, of course you need to have a model that will be strong enough, to be robust and you, in some sense, learn the artifacts, but it's just the first phase of the game. And the idea is to organize this kind of challenge, to work together on a specific challenge will be devoted just to learn this kind of stuff in order to generalize enough in the future. For phase, of course, there is a strong bias that you, in some sense, mentioned, to the fact that, of course, the phase is, you learn also a specific structure, because a phase, of course, is done always in the same way. Okay? And when you generate or you try to detect some artifacts, of course, there is a bias due to the fact that you are searching for phases. Other works tend to be more general. In that case, you lose the structure of the phase. Imagine that some recent work in the field have found that some detector of deepfake concentrate the attention not on phases but on background, just because the signal with respect to the specific phase is always the same. There is a lot of work to do. There is a lot of things to learn together, and also taking into account the role of the community, we hope to be better in the future.
Just one observation. Do you know, there are also those kind of deep fakes that completely reconstruct both background and foreground. The so-called reenactment-based deep fakes. In this case, we have a complete puppet with background and foreground. This is a further challenge to be faced with in the future. Thank you once again. If there are no more questions.
Thank you. Other questions? Okay, thank you.
Slide.
Okay, sorry, we conclude this this session with this last slide in which we present the. No.
1 moment, please.
Okay. Okay, in this slide we present the first forensic summer school called IFOS, International Forensic Summer School, and with 3 directors, the school directors, the Professor Sebastiano Battiato, full professor at the University of Catania, the Professor Donatella Curtotti, full professor at the University of Foggia, and the Colonnello Aldo Mattei, law enforcement of Carabinieri. And in these slides you can see that several speakers, there will be in the summer school, and several advanced topics will be discussed in the in the summer school, like forensic evaluation in court of biometric data, forensic defect detection, double identity biometrics, and others. Okay, thank you for your attention, and basta.
Hi. I would like to thank you for, grazie Luca.
Thank you.
I would like to thank you again for participating in this session. This concludes the first day of conference. I would just to remind you the welcome dinner at Convittor Palmieri, that is the location of the workshops, and 7:30. Thank you again.